This is This Week in Science and Education, episode 26, Lucy in the Sky with Comets. It's time for This Week in Science and Education, the show that talks about all things health, research, and science, and academic discovery. And if you're a teacher or a student out there, this show is for you. How do you take that information, bring it into the classroom, tell your students about it? Today we're going to talk about Lucy, the million-year-old woman. All that today and more coming up next on This Week in Science and Education. This Week in Science and Education is brought to you by Polycom, world leaders in unified communications. Polycom.ca. And by Mueller Systems. Need a backup? Check out MuellerData.com/VROC. That's MuellerData.com/VROC. It's time for This Week in Science and Education. This is your host, Kevin Cougler, broadcasting from the University of Western Ontario. Thanks to everybody for joining us today. We have a very exciting show. Rather than interviewing guests or taking questions, we've opted to do a relevant and most recent news type of podcast today. We're going to talk about Lucy walking tall, foot in her bone causing her to do so, perhaps, and comets. So really, Thomas wants to interject.
I think, in fact, you meant to say bone in her foot, not foot in her bone.
Foot in her bone.
Oh, no. Editing already. This isn't good.
Just for clarification.
Well, thanks for that, and I guess now I'll have to introduce you first. So, ladies and gentlemen, the fellow that always keeps me honest, the mad scientist from Laurentian University, Sudbury, Ontario, Dr. Thomas Merritt.
Kevin, I take it you had your coffee for today.
I'm good.
There you go,
Jack.
I think you went to a hockey game on the weekend too, by the sounds of it. Or a wrestling match.
I was doing my Johnny Carson impersonation. What do you think?
Yeah, don't lose a day job. It's good to see you, Kevin.
Mommy. Oh, I know you hate that one. I know. All right, back over to Colin, Kawartha Pioneers District School Board. This show is going downhill fast. I think we should just start again.
3,
hey, Colin.
2, 1.
Hey, everybody. How are you?
Good. Doing well. So, Lucy, walking tall. This is an interesting news item that we came across. So this is out of the New York Times. And the author of the story, a lady by the name of Cynthia Banu, hopefully I pronounced that correctly. It was published on February the 11th of this year, so just a little while ago. I'll read the first couple paragraphs, then I'll open it up to discussion, guys. So the article talks about Lucy may well be the world's most famous fossil hominid. Oh, here comes this word that I don't know how to pronounce, so this is going to be fun. She is the best-known... I'm going to get Colin to do it. Good stuff. She's the best-known specimen of the species
Australopithecus
afarensis. Yeah!
Pithecus afarensis. There we go.
AA. Let's just call it AA. Species AA. And her partial skeleton, found in 1974, revealed that she and her kin could walk upright. So this is quite interesting because, of course, this is millions of years old. But because of a lack of a foot bone specimen, scientists have long debated how well she walked. That is, whether AA also used a grasping movement with the feet. So that's kind of interesting. So she was walking upright but also could grasp things up off the ground with her feet. Now, a fossilized foot bone from Hader, Ethiopia, reveals that AA had arched feet, as do modern humans, and was fully committed to walking upright. And species lived between 3.7 million and 2.9 million years ago. And the first thing I thought was, wow, that's even hard to fathom just in itself. The science aside, like 3.7 million years ago, our modern civilization is only 3,000 to 4,000 years old. To put that in perspective is just incredible. Colin.
Yeah. What do you want? I mean, Lucy is sort of, it's the archetype for human evolution and bones and our understanding of our ancestors and where we came from. And they piece together these stories by finding, like, literally little bits and pieces of bones that they then date from, this is, roughly 3 million years old, and finding all of these bits and pieces and slowly putting together the story of what this species would have been like, and what their life would have been like, and what they ate, and how they traveled, and all of these various pieces. And with this particular story, they found a metatarsal, which is one of the long bones in your feet. And apparently there's been a long debate over whether Lucy Lucy is the name of the particular skeleton, but Australopithecus afarensis was able to use their feet to grasp. And if you've ever seen, like a lot of modern primates can do that now. They can actually grasp onto branches and whatnot with both their hands, and their feet as well, right? And that was the idea that they didn't know if the foot had that ability to be able to grab onto things and either maybe pick them up or grab onto branches when you're on trees and that sort of thing. But when they found this metatarsal, it suggests that just the structure of it, it's more sort of modern human than it is primates who can grasp with their feet. And so that really suggests that because of that Lucy pretty much walked mostly upright, and also then didn't have that grasping capability. So I mean, it's a small bone that tells a really big part of evolution, sort of leading from previous primate, strictly primate ancestors towards a more modern human. And again, like you said, it's 3 million years old. It's always astounding me that we can piece together these little tiny pieces one bit at a time.
It seems, Thomas, it seems amazing to me that you can take this little tiny bone and infer all of this information from it. It just boggles my mind. How do they do that?
Magic. It's a really neat story, and it's a really neat story on a number of different levels. I can remember learning about Lucy as a student, right? And so she was the original discovery was 1974, and so by the time
the Leakeys, right? Found that one.
Yeah, I think you're right. And so, 10 years later, when I'm in high school, this is one of I can remember being in social studies, right? And social studies included anthropology, and part of anthropology is we were studying the human ancestry. And so this particular fossil is one example of the species, and it tells us something about the lineage through which modern humans evolved. But it's also a neat rallying point for science. It's the kind of things that kids get excited about. I can remember getting excited about it. When I went to university, graduated high school, off to university, friends of the family gave me some books and things, and one of the books I got was this story of Lucy, because they knew I was interested in science, and this family thought this was one of the most exciting stories in science, and so they had sent that. So this particular species, the Australopithecus afarensis, is just, we think, one of the stepping stones, or it's one of the phases that human evolution went through. But to our culture, I think it means a little bit more than that, because it's been such a rallying cry for science. It really means a lot to us as a group. How do they infer this from one bone? They don't. And that's sort of one of the really neat things about this particular story is we've inferred quite a bit about how Australopithecus afarensis lived. We know quite a bit about their skeletal morphology, how they would have walked now. We know, brain volumes. We get an idea of what kind of mental capacity they would have had. Do we have all of this from single bones? We don't. We have different parts of the story from different bones. And this one bone gives us a really interesting view on how this species likely stood and walked. And it's an interesting story because we pretty much were able to infer from other bones that Lucy, or that her species was standing upright. Mm-hmm. But other primates stand upright. And the question is just how dedicated to standing upright was this particular species. And it's sort of exciting that these fairly fundamental things we don't know. When you look at the evolution of birds and flight, and at least a few years ago when I was still following the story a little bit, it was an open debate as to whether flight started with birds running and taking off, so it ground up, or whether birds climbed and glided down, So was it a ground-up evolution of flight, or was it a glide-down evolution of flight? And that's a pretty fundamental question, and we don't know the answer to that. So this particular case with afarensis, were they dedicated to walking? Were they occasionally walking? And this particular bone gives us a really neat idea that it looks like they were dedicated to walking. So Colin was talking about the idea of grasping versus not grasping. If you look at modern primates, they can, for periods of time, walk in a bipedal upright fashion, but they don't dedicate themselves to that. They can also walk around in trees and swing from trees in a way that we can't. And so there's this advantage to having feet that will grasp onto limbs. If the species has evolved to be dedicated bipeds, then there's advantage to having a permanent arch to your foot. And that permanent arch to the foot, it absorbs strike forces as you walk, and it gives you more power as you push off. Now, keep in mind I'm a geneticist, and so I'm almost making this up. But, I mean, that's sort of loosely what's going on.
As opposed to most things we talk about.
As opposed to most things we talk about. So this one little bone gives us a much better idea of how this foot sat on the ground. And everything that we have from that evidence suggests that there was a permanent arch. If there's a permanent arch, that's an organism that has a dedicated lifestyle to bipedalism, to standing upright. Right? Now, that's this one bone. How do we know all these other things about Lucy and any fossil in general? It's from piecing all of these together. One of the really exciting things as a working scientist to look at how other people do this. When I'm working on one of my genetic systems, I have the entire system in front of me, and it's a matter of teasing here, working on things to tease it apart. With people working with the fossil record, you have a fossil here, you have a fossil here, you have a fossil here. How do you know that this fossil goes with that? So Lucy was particularly exciting because she was such a complete example of that species. Right? But still incomplete enough that we didn't know whether she was standing upright because we were missing this set of midfoot bones. How do we know that this midfoot bone belonged to Lucy? Right? Well, there's a really good chance it didn't. There's almost no chance that this bone goes with that skeleton. Right? Of all the thousands or maybe millions, I don't know what our estimate of population size for afarensis was, but almost certainly this isn't part of that. Part of that skeleton. So if you don't find that bone with the rest of the skeleton, how are you able to associate this bone and what it tells you about its person with other examples of this species? And so I read through the paper a little bit, and it's pretty neat. What they did was there's a particular horizon. They're actually sifting through soil that's eroded out of a particular layer of the earth. They know the layer that it's eroded out of, and so they're seeding over here, but they know that it came from here. They're able to date that strata, that layer, to the 3.7 to 2.9. They've looked at, I think they said 370 specimens that have been identified as hominids from that layer. Every single one of those specimens that they can identify to species is afarensis. So, does this bone that's novel and unprecedented and hasn't been found in other fossils, is it afarensis? We don't know. Is it likely to be afarensis? Yep, because all the other examples from that strata that are hominid are afarensis. And so that's a long answer to get back to your short question. How does one bone tell us so much, or how do these different bones tell us so much? It's only when we work with them together. And the really exciting thing, as I said, as a working scientist, to look at how other scientists are doing this, is how they were able to do that. Can they guarantee this is afarensis? Nope. But given everything that we have, that this looks like it's a foot bone from afarensis. Can you guarantee that this bone means that whoever had the bone was standing upright? Nope. But everything we have is consistent with that bone, meaning this was an arched foot, and an arched foot means that you're a bipedal organism. If you're a bipedal organism, there are advantages to your stride, to absorbing shock. You're a more efficient walker. Watch a video of a chimp walking on 2 feet versus people. Right? Well, that's the trade-off between those two. Now, the trade-off is that afarensis would have been less likely to be swinging through the trees, but more likely to be able to run like the wind. Right? So it's a neat story. It was fun to read through that. It was fun for me because, it brings back high school 2+ decades ago of getting excited about Lucy and what Lucy told us about our own human evolution.
Well, and if you're excited about that, 2 years ago, we have the story about Arty. that came along.
Yeah.
And Arty was, I guess, is it carbon dating that they're using here to determine
amongst
the age?
other things? Yeah, amongst other things. Carbon dating only goes back, I think, several tens of thousands of years, so it'd be other kinds of dating, including, like Thomas mentioned, where it's found in the geology and dating the rocks. You know, so there's a bunch of different methods. But yeah, that's how they get some of these dates.
So they estimated that Arty lived about 4.4 million years ago.
Yeah.
And Arty was part of the Ardipithecus remedus species. And the interesting thing there for me was from 4.4 million years to 3.7. That's what, 700,000 years or so that it took for, you know, our ancestral or part of our ancestral tree to actually go from walking on all fours to walking upright. So it didn't just happen overnight. It took thousands and thousands and hundreds of thousands of years. But that's you know, that was quite striking in terms of that timeline. Have you got some visitors over there, Colin?
Oh, I know. It's a busy spot around here today. It's a bit noisy. Sorry about that.
No problem. Anything left on that, guys, or should we do a break and come back with our second story?
Let me just do one thing. So if I were teaching about this system in my class, you know, one of the things you had this idea of picturing a chimpanzee or an orangutan walking versus picturing a human being walking. The difference is this permanent arch versus a flat foot. Well, we have flat feet in humans, fallen arches, right? And so it's the kind of thing that a student might say, well, is this the same? Is the chimpanzee foot or the more primitive or less derived foot, is that the same as fallen arches? So it's the same flat foot, and it's the same painful walking or not as efficient shock-absorbing walking, but anatomically it is completely distinct. And so it's one of the points that the authors make in the paper. And I think the point that they're trying to say is that if they had found bones that were consistent with a flat foot, it wouldn't be pathology. It wouldn't be that they happened to find a Australopithecus afarensis with fallen arches. Right, so the bones are distinct, although the final outcome is the same of having this flat foot. If you think of things like fallen arches and flat feet, anatomically that's distinct from what we're looking at here. And so this signature of the bipedal arch or this arched foot is different from things like medical pathologies. And that kind of thing does come into play. If you remember the story from a couple of years ago of these very small fossil people that were found in an island population, a number of the skeletal characteristics for those species were consistent with pathologies. So with essentially things like dwarfism, not having evolved into a certain stature, but actually a pathology that was making their heads small and stature small. So there are ways that we can look at a fossil and say, is this a signature of a general trend in the species, or is this an example of some sort of medical condition? And that's the kind of thing I bring into my discussion in the classroom. You know, what can we learn from these fossils when we compare them to modern fossils or modern bones?
And you're exactly right. And the Hobbit story from a few years ago, that's still sort of up in the air whether that was a pathology or whether it's a signature of that particular species or not. Just one other thing sort of struck me, Kevin. You talked about the 4.4 million to 3.7 million, sort of that transition. It's also a good teaching point to keep in mind that these two species may not be directly in line, right? They're previous ancestors, but they may not be directly related to each other. Right, that's the tree of life, or the bush of life, as it might be more aptly called. That these things could have existed side by side, having branched out from somewhere else, right? And the fossil record is incomplete to the point where we know so much about them, but we can't make all these distinct things. So Arty may not have been a direct predecessor to Lucy. So those things were maybe happening together in different ways, right? So it's always interesting to keep in mind and bring all of these pieces together as we piece together this multi-million year history.
Yeah, and that's a really good point. I mean, you want to be very careful about not saying these are stepping points on the way to human evolution. These are different species that evolved, but they're not moving towards anything. They're just different examples as we move along the spectrum. One example of hominin species is modern humans, but it's nothing to say that these were steps on the pathway to modern humans.
Yeah.
Another 3.9 million years pass, and we might just be a blip on the radar to somebody at that time period as well.
Might.
So, yeah.
We're certainly doing the best we can.
We sure are.
My pool's going to need a new cover by then, I can tell you that much. Anyways, coming up, NASA's second close encounter with a comet. We learn all about Tempel 1 comet and how NASA got to visit it twice. Rather interesting. We'll have Colin introduce that one, since I know, Colin, you're really interested in space. You're the space geek of the crew, which is fantastic. But before we get to that, I do want to talk about our friends over at Mueller Systems. Muellers are the company out of Woodstock, Ontario. If you need a backup, you've got some important documents to make sure they're protected and taken care of, log on to muellerdata.com/VROC, and you'll be able to enter into a 90-day free trial and try out their backup software. And it doesn't end there. They will help you configure it and test it and make sure all those documents are getting backed up properly, so that in the case of a catastrophic failure, such as comets striking the Earth and wiping out your house. See how I'm segueing here, guys? This is pretty cool, eh?
Yeah, that's a nice natural one. I like that.
Because it happens every day, Colin. We got stuff hitting the Earth. Anyways, it could happen. You never know. Your data will be protected. Check out muellerdata.com/VROC. We thank them for their support. All right, part 2 of the show, NASA's second close encounter with a comet.
Mm-hmm.
Go ahead, Colin.
Yeah, this is an unfolding story as we speak. This is what's really neat about doing this one today. There's a long history to this one, because back in 2005 there was a NASA space mission called Deep Impact, named stupidly enough after the really bad movie that talked about comets striking the Earth. Right? I guess it was just publicity choice of name on this one. But this was a really cool mission back in 2005. No, not at all. Any publicity is good publicity, right? So what they did with the Deep Impact mission was they sent this spacecraft called Deep Impact out to visit this comet Tempel 1, and they had on it an 800-kilogram copper projectile, which was basically an 800-pound copper chunk, essentially. And so the comet was coming this way, and I see my hands here in the spacecraft, little tiny spacecraft coming the other way, and before it got to it, it released the piece of copper and then sort of shot its rocket engines and sort of just moved away a little bit, and then basically the copper piece ran into the comet, right? And the spacecraft took photos of it while it was doing that. The purpose of this mission was to basically see the inside of a comet, to try and dredge up some fresh material inside the comet, do spectroscopic analysis of it through photography and remote sensing, and try and figure out what's inside of a comet. We'd taken pictures of surfaces of comets before, but never really been able to sort of get at the underlying crust, because comets have like a hard, dark crust on the outside. And so the inside of them is a bit of a mystery. So that's what this mission did. Yeah.
Sorry, I just want to interject. The reason that we do that, of course, to continue with the movie analogies and comparisons, is that when Bruce Willis has to land on that comet in the future and blow it up, we'll know how to get in there and do it. Okay, just thought I'd interject that.
Yeah, that's exactly why we do these things, Kevin. So it's good that you're up on the modern science end of things. It's really, really impressive.
And the show will be hosted by somebody else next week. We'll let you know who that is.
That's right. We're going to get an actual scientist on the show next week. But I was in the classroom at this point, and this was a really cool thing, because people on the ground observed it. People with telescopes on the ground were taking pictures of, because basically the comet got brighter as material started to spew off of it, just like a comet naturally would get brighter as it gets closer to the sun, and you get the tail developing and that sort of thing. So you had the spacecraft taking pictures of it, people on the ground taking pictures of it, and they learned quite a bit about the material in a comet. Of course, because all this explosion happened, by the time the explosion and the dust sort of settled around the comet, the spacecraft and the comet were no longer near each other. So they couldn't get any real good pictures of the long distance after effects. Okay? So then we move ahead to another mission called Stardust, which was, I'm trying to think, it came back to the Earth just a few years ago. I don't have the date. 1999 that was launched? Okay.
Yep.
And Stardust was another really cool mission, because what Stardust was they went out to basically capture pieces of a comet. It had like this tennis racket kind of looking thing with an aerogel. You guys familiar with aerogel? It's like a really lightweight kind of stuff. Picture like a gel, like a Jello kind of material, but really, really light. And so what this thing did is it flew through the tail of a comet, a different comet, put out this tennis racket kind of thing, and caught bits and pieces of the dust coming off of the comet as it flew through. Then it pulled it all back inside. And then
wow, that's cool.
Yeah, and then the spacecraft came back to Earth a few years ago and parachuted down into the desert, where scientists then, and actually it sort of crashed into the desert because the parachute thing didn't quite go so well when it came back. But they were able to rescue a good chunk of it and get some pretty good science out of it. So actually pieces of a comet were brought back to Earth by this Stardust mission, which was really cool. So then the Stardust mission said, okay, well, our spacecraft is still working. The cameras are still working. It's still doing all of the things it's doing quite well. What else can we do? So they got looking at orbits of comets and stuff in the solar system, and they realized that with a few minor course corrections, the Stardust mission could intersect with the comet that Deep Impact had already intersected with, right? And so then they started planning this extension mission. So basically, yesterday, the spacecraft finally caught up with the comet and took pictures of the comet, including the crater that Deep Impact had made like 6 years ago. The dust has all since cleared, so now they're going to get to compare the surface of the comet before and after. Because one of the things that when you look at comets, you see craters on the surface of a comet, so it's very kind of it's a moon-looking kind of place where there's craters and impact scars and that sort of thing. But you could never sort of tell the ages of them. So now they know for sure the date in 2005 that this particular crater was made, and they can compare it with all the other ones and sort of make some analysis then over how comets behave in their lifetime, the kind of things that they undergo, all that sort of stuff. So it's a really neat story, and the neat thing about it is I'm sitting here now, my computer's finally back up. The photos are coming in right now. Like, they're literally coming in as we speak on the Stardust website. And there's
What's
photos.
the address, Colin?
I'm on the NASA website, so it's nasa.gov/Stardust, I believe, is where I got it from. And
little picture of Willie Nelson beside him there and everything.
No, there's not a picture of Willie Nelson.
Yeah, there are a lot of people that are going to pick up the Stardust reference there, Kevin. Good.
Yeah,
that one's going to be ubiquitously understood.
Generational one.
I was going to say that might be your highlight for the current generation. And of course, these are unprocessed images, right? It's going to be neat once the scientists have some time with them, get a look at them. Because I mean, right now I'm looking at it and
you can Photoshop anything.
You could. I was actually using Photoshop earlier today. I was comparing the pictures from Deep Impact originally with these ones, and I can't see anything, right? I'm not sure where to look, but once actual astronomers get a hold of these images, they'll be able to point out, look, this spot right here is where the thing hit. Here are the differences before and after. So I'm really looking forward to sort of the pictures and the analysis as it comes out, because this is a pretty cool, like, happening live right now. And you mentioned about bringing it in the classroom. If I was in the classroom today, this would be on my screen. I would be showing kids these pictures as they arrived at the Earth, because they started sending them back last night after they took them all after the flyby.
It's an amazing thing. I mean, the timeliness of that is exciting, and it's the kind of thing that you can directly become involved with. I thought, Colin, your point about be able to age things is, we were talking earlier about it's amazing the things we don't know. Right?
Yeah.
When you look at a comet and you can see these craters, and we don't know what the age of them. So the point they were making in the brief article was, are these hundreds of years old, or are they millions of years old? Right? And we'll have something to at least to work off of. And then I think there was a neat point the article finishes with, is that in addition to not knowing the age of them, we don't know how many of these craters are being caused by impacts versus explosions of things that are vaporizing from inside, and that'll give us another view of that too. But yeah, the sort of science in process, the images coming up now, it's a fantastic opportunity.
Yeah, and that's always struck me so cool about, like, NASA in particular and some of the NASA missions is the stuff they do. They basically make it public in real time, right? You can go and get from whether it's a Mars rover image or this one from Deep Impact, but they put those things on their websites as soon as they come in. They're raw, they're unprocessed, and of course once they get into a press release later, people they clean them all up. But being able to look at that stuff kind of first and in real time is really amazing. I mean, I remember a couple of years ago when the Huygens probe landed on Titan, which is one of the moons of Saturn, and it parachuted down and it took pictures for the first time of the lakes and rivers and systems on Titan that were not a hydrologic cycle, but a methanologic cycle. It's methane rivers and lakes on the surface of Titan. And I remember watching those in real time with my class as they came in on the screen and talking about them and saying, well, what does this look like to you? I said, well, it looks like a lake and a coastline. I go, well, that's what it looks like to me, too. I don't know what it is. Nobody else does yet either. But we're seeing these pictures as they come in real time, which is just so neat to be able to look at that stuff and say, what do you think it is? Right before the scientists kind of make their quote-unquote official announcements of what they are, where they really analyze them in depth. But showing kids you can do it in real time and be excited by it is just really fun.
Colin, you are one of those teachers that I wish that I had when I was in school, you know that, because you're right up on this stuff, and it would just think about this, you know. I don't know if you probably didn't get a chance to see the show this morning, but on This Week in Technology and Education, we talked about the announcement by President Obama in the U.S. that 95% of the United States would receive wireless internet coverage in the next 5 years. Right. And just from an education perspective, we talked about what does that mean for the classroom. Well, if you're a world of Collins out there, it means that 95% of the classrooms, whether they're rural or urban or whatever, will be able to see stuff like this because they have Colin's passion and energy, and they're going to bring this information that day as it's happening into the classroom. So, seriously, you're laughing, but I applaud you with that.
I can't even imagine.
Anyways, gentlemen, anything left on that article, or is that a show for today?
You know what? There's lots left to come, but we have to wait until we get some official processes and, you know, people with knowledge to point out arrows on the picture and say, here's where it is. So we'll come back to that maybe and just look at some of those photos next week or something.
Sounds good. Well, we'll watch that with interest, and we'll throw a link up on the show notes on the website, and that website again is twice.vrock.ca. Go there for all of the latest show notes and announcements about who future guests will be. And on behalf of Colin Jagoe from the Kawartha Pine Ridge District School Board and Dr. Thomas Merritt from Laurentian University, this is Kevin Cougler signing off and thanking you again for another fantastic show. See you again next week, everybody.
Thank you.
See you next week.